Okay, in this presentation, what we're going to do is look at hypothesis testing. And what we're going to do in this particular example is look at the difference in proportion. So what we are dealing with here is a two-sample test, and we're looking at proportions. Okay, now I'm going to sort of cut out a bit of the discussion, just for the sake of brevity, and just remark that we have two samples, A and B. Okay, and A might be, let's say, one city and B might be another city, something like that. We have a sample of 200 in sample A, and out of that sample we have 140 successes. Okay, and likewise for sample B, out of 180 cases we have 108 successes. So immediately what we could do here is calculate the point estimates for both samples. Okay, so P, the point estimate, the sample proportion for A is 140 over 200, and that is 0.70, or in other words, 70%. For B, something similar, the sample proportion is 108 out of 180, and that is 0.60, as in 60%. Okay, something like that. Okay, so that's all well and good. What we're going to do now is actually see if we can use this for hypothesis testing, okay? Or essentially set up a little hypothesis test based on this, okay? So essentially what we're interested in is the true proportion of all the entire population for A. Is that equal to the true proportion for the entire population for B? Not just based on the sample. Can we use the sample that we've just created to make inferences around the entire population? Okay. Now the null hypothesis is PA equals PB. That's the true proportion of A equals the true proportion of B. And just write a little discussion there. Now I didn't really give a context, but actually just write a little sentence there that there's no difference in the true proportion between A and B, and so on. Okay. Don't forget that little step there. I mean, I sort of, just for the sake of brevity, I've cut it out, but you should include that in your answer, okay? So the alternative hypothesis is that they're not equal. Mu A is, or PA is not equal to PB. Okay, so that could be expressed as there is a difference, or they are not the same. Okay, so that's just a sort of quick remark. Sometimes the true proportion could be actually denoted as pi rather than p. Okay. Now, so just actually a remark upon this. This is a sort of, I'll just sort of skip back here. PA is equal to PB. Now that's the null hypothesis. So I'm just going to move on to the next page here. PA minus PB equals 0. It's essentially the same thing. PA minus PB is equal to 0. So we're expressing a difference. We're not sort of saying, well, it's sort of the same thing, but we're making more clear now, but we're talking about a difference here. This is a difference. The difference is equal to 0. The difference is not equal to 0. Okay, so that's what this question is framed as. Now, with regards to the hypothesis test we're going to carry out, this difference is our point estimate. Okay, so we have a point estimate there of 10%, 0.10. Okay, so let's just sort of go back to our little point estimates here and just actually add that to our list. PA minus PB equals 0.10, as in 0.70 minus 0.60, as in a 10% difference. Okay, that's going to be our key point estimate for this actual calculation. Okay, now let's move back. So it's essentially we have it expressed as a difference here. So the difference, under the null hypothesis, we expect a difference of 0. Okay, so now we're going to move on to the test statistic. Now the test statistic is straightforward. Well, mostly. First off, we have the point estimate, which we just seen there to be 10%. Okay, let's add that in. We'll work on the basis of percentages, just because it's a little bit easier to calculate. Now, under the expected value under the null hypothesis, or in this case, the expected difference under the null hypothesis, as I just sort of stated there last, it is 0. Okay, under the null hypothesis, we expect a difference of 0%, no difference. Okay, so the last part is the standard error, and this is where we go to our formula sheet. Okay, so the PA minus PB, Okay, so 10% over our standard error. Okay, so that's our test statistic. Now this is where we go to the formula sheet. Okay, so formula sheet. Okay, now what we should get is something like this. Now this is actually, just watch out for this when you're dealing with hypothesis tests. Okay, you actually would have there's a difference between hypothesis tests and confidence intervals when calculating proportions. Have a look at your formula sheet and see if you see that. Now, the overall structure of the null hypothesis, or the confidence interval for the standard error for hypothesis test is this. Okay, p bar times 1 minus p bar all over NA plus p bar times 1 minus p bar all over NB. Okay, now you can shorten that. It's a sort of algebraically the same, but just sort of factorize it a bit. So this is the actual version I actually give in my exam papers. This one here. This is a little bit shorter. It saves you carrying out unnecessary work. Now, but what is this p bar? This is the pooled or aggregate proportion, actually, probably better. The aggregate proportion. Okay. Okay, and what is that? It is the total number of successes over the total sample size. So it disregards which sample. Okay. It disregards which sample it came from. Okay. So just like, let's look at everything all over together. So how we calculate that? P bar. It's really, we had 140 successes from A plus 108 successes from B. So that's 248. All over, we interviewed 200 people in A or whatever. We have a sample size from A of 200 and a sample size of B of 180. So the pool proportion is 248 over 380. Let's calculate that out. I'm going to sort of state that as 65.26%, okay, working on the basis of percentages. So that gives me my pooled proportion, and that's what we use in our standard error. So let's calculate out the standard error. So it is 65.26 times the complement of that, which is 34.74. Okay, and that's p bar times 1 minus p bar, the complement of the p bar, all over 1 over 200 plus 1 over 180. Okay, that's it there. Bit of calculator work. Let's work that out a bit. Square root of 2267.13 times 0.01055. Okay, that essentially should be the square root of 23.91, which is 4.89. Let's just leave it as 4.89. If you don't get exactly the same answer, I'm just sort of shortening it in. Okay, a little bit of rounding error. But anyway, that's my standard error. Okay, the standard error is 4.89. Okay, so let's go back and calculate our test statistic now again. Test statistic is 10% minus 0% all over 4.89. Working that out on the calculator. Sorry, I just have this done off screen here. We should get slightly more than 2.045. 2.045 is what I make that to be. That's our test statistic. Now, critical value. I'm just going to remark that this is a large sample. It's a two-tailed test. And let's just say, I didn't actually state this earlier on, but the significance level is 0.05. And in that case, our critical value would be 1.96. So that's our critical value, 1.96. So, finally, the decision rule is we compare our test statistic to our critical value, The decision rule, as always, is the absolute value of the test statistic, TS being test statistic, greater than critical value? Is the absolute value of 2.045 greater than 1.96? Yes, it is. We reject null. Okay. So that means that there is a difference between population A and population B. Okay. Now, for the sake of brevity, I cut out a lot of context, but don't forget the context. Discuss your answer or give your answer, put some related to the context of the question. Okay. Okay, that's it. Okay.